Now the second part of this experiment is to observe the clamper. The circuit made over here is as given in the handout for the clamper. In the clamper, first we are making the VB equal to 0 for simplicity as given in the handout, and we can observe the waveform on the DSO. Here also we are giving an input of 1 kHz sinusoidal and 15 volt peak to peak from the function generator to the circuit. Now we'll give a power supply. Here the yellow one is again the input, the blue one is the output. We can see the input being shifted on the downside as can be seen in the waveform. So that is why this circuit is known as clamping circuit. Now we start giving the input from the power supply to the circuit. We can change the voltage range through the second segment of this power supply. Currently it is showing a -2 volt supply to the circuit. We can increase it to -5 volt. As can be seen on the DSO, as the voltage is being increased for the negative part, that is being decreased to a lower value. As we approach to -5 volt, the clamping is seen more. That is, the waveform is being shifted more downwards. Now the same circuit can be again applied to observe a positive clamping, that is the output will be shifted upside. Now we will provide a positive voltage to the B, that is shown in the handout. Now as we increase the voltage to 5 volt, we can see the waveform on the function generator, the output being shifted upwards. Hence, we can see the clamping part for this circuit that is being performed by the circuit, and the waveform is being shifted upwards or downwards depending on the value of the power supply that we are giving to the circuit.
This next circuit is the op-amp differentiator. The input is still applied to the inverting terminal through a capacitor C, and a feedback resistor of R is present that connects it to the output. The non-inverting terminal is grounded, and under these circumstances the equations that apply are the following. V minus, which is the inverting terminal voltage, is the same as V plus, the non-inverting terminal voltage, and they are both equal to 0. So the current that flows through the capacitor, on account of the high input impedance of the inverting input of the op-amp, is equal to the current through the resistor, and the capacitor current therefore is given by C dVi by dt. Now this current flows through the resistor and takes the output voltage to below the ground voltage to an amount equal to -Ri of t, which comes out to -Rc dVi by dt. So this is the differentiator, and here is what you do when you feed an triangular wave as the input to the system. The derivative of the triangular wave is a square wave, because it consists of segments of constant slope, and wherever the slope is positive you get a positive constant value, wherever the slope is negative the output gives you a constant negative value. So the output you would observe is a square wave that superposes with this in this manner. This would be a proper differentiator, but what actually happens is the inverse of this, because this again is an inverting differentiator. So the output you would get is not really this would be the output, actually it's minus of the output. The actual output would be this. This is the actual mu of t. The inversion of the derivative, of course, with some constant of proportionality called Rc in this case. So when you carry out the experiment, you will apply an input of the specified frequency, observe the output, put them all together and see if the output is an inverted derivative of the input.
Now the other part of this experiment is to perform the differentiator circuit and observe its output on the DSO. For this experiment, we are giving a 100 Hz triangular shaped input through the function generator to this differentiator circuit as given in the handout. The resistance and the capacitor values are used that are mentioned in the handout for this circuit. So we can observe the input and output on the DSO. Like in the DSO we can see that there is a yellow segment, that is the input, which is the triangular shaped waveform to this differentiator circuit. The blue one is the output waveform generated by this circuit for the input given to it. Since the input given is a triangular shape, hence the differentiated output is coming out to be a square wave as shown in this DSO. Here the input is being given to the inverting terminal of the op amp. So we are able to observe that for the positive slope, the negative cycle for the square wave comes for the positive slope of the input signal. Hence the circuit differentiates the input and the differentiated output can be observed on the DSO.
This circuit is the op-amp based integrator. Its function is to produce an output waveform VO of t that is proportional to the time integral of the input waveform. Because it's an integrator, care has to be taken that the input waveform is zero average. If this is not the case, the output will go on rising or falling endlessly until it hits the saturation voltage and stay saturated. So maintaining the input signal at a proper zero average DC voltage is very, very important. Assuming that we have done so, here is how this circuit works. Very simple. The non-inverting terminal is grounded. Hence, because the op-amp is working in the linear region, the inverting terminal is at virtual ground voltage, and a current flows in from the supply Vi of t equal to I of t given by Vi of t by R, because this is effectively at ground voltage. That current flows through this C and makes contact with the output. So the output voltage is essentially the negative of the capacitor voltage, because it is the current flowing from left to right makes the right plate of the capacitor go below the inverting terminal voltage. In short, then, VO of t equals B minus of t, which is the inverting terminal voltage, minus of the capacitor voltage. Capacitor voltage is given by 1 by C 0 to t integral I of t dash dt dash, I t dash being the current. For the time being, please ignore R dash. We will come to it in a moment. And this, on substituting for IT, gives us minus 1 by RC integral over time Vt dash dt dash. So this is the integrator. So if you apply, for example, a square wave as the input, then you will observe an output that integrates the input signal. So when the input is positive, this should have gone positive, but because there is a minus sign here, this is really the negative of an integrator. So what you will see here is this. This is the integrator's output. It is the negative of a proper integrator because its input is being fed at the inverting terminal. So all that happens with an inversion. So now let's come and look at why R dash is present. I had said earlier that in the case of an integrator, care needs to be taken that there is no residual DC component in the input, because if there is, it will integrate in the same direction continuously and cause the integrator to saturate in no time. Hence, when the capacitor keeps undergoing these alternations in voltage, this resistor ensures that any offset that might be present in the input side does not lead to an endless integration of a DC offset voltage onto the output, and hence prevents the integrator from saturating. So this resistor R dash is normally a large value, and it's just sufficient to ensure proper operation of the integrator. So when you do the experiment, you apply a square wave voltage at the input and observe the triangular wave that should appear at the output. You will see that if you change the amplitude of the square wave, the output also changes in amplitude correspondingly, and the proportionality constant can also be verified that it is 1 by RC if you wish.
Now we are going to implement the integrator circuit using the op-amp. Here the signal that is being given as an input to the circuit is a square wave pulse of 25 kHz frequency and 4 volt peak to peak. The integrator circuit basically integrates whatever the input signal is. Since the input is a square wave pulse, hence the output of the integrator circuit should be a triangular wave pulse. Since in this integrator we are giving the input to the inverting part, hence we can observe the waveform on the DSO. Here the yellow one is coming, yellow is showing the input signal, that is the square wave pulse, and the blue one is showing the output waveform, that is the output of that circuit which is being integrated by this circuit. Here the integration output is being shown. The slope is negative because we are giving the input signal to the inverting side, hence the slope is inverted for the output signal.
So the next circuit is this astable multivibrator. This circuit, unlike the previous op-amp circuits we have studied, except for the Schmitt trigger, works in the saturated mode rather than in the linear mode. So the output of this op-amp at any time is either plus Vsat or minus Vsat. Never at any value in between except very, very momentarily. So let us see how this circuit works. Fundamentally, an astable multivibrator is nothing but a square wave oscillator. It's a circuit that is never comfortable either when the output is at plus Vsat or when the output is at minus Vsat. Whichever state of the two you put it in, very soon it shifts over to the other state and then shifts back and shifts forth and so on indefinitely. So this now is an explanation of how this works over here. Now this is R1, this is R2 and this is R2 dash. These three resistors jointly form an adjustable potential divider. So this is a potentiometer R2 dash and it allows it to be adjusted, and to the extent that R2 dash can be adjusted between 0 and 10 kilo ohms, K varies from a minimum of R2 by R1 plus R2 to R2 plus 10 kilo ohms by R1 plus R2 plus 10 kilo ohms. So this is one of the adjustable parameters of this circuit. The other adjustable parameters are C and R. Now let's see what happens. How does the circuit work? At any moment of time, let us assume that the output voltage is, let's say, minus Vsat. Now if the output is minus Vsat, then because of this potential divider, V plus equals K times minus Vsat. This is the non-inverting terminal voltage. This acts as a threshold reference with respect to which the functioning of the other side of the circuit is determined. Now, if this is at minus Vsat and this is at ground voltage, clearly the capacitor has an opportunity to charge, because the capacitor will charge to minus V